Hi, in this video, we're going to look at doing some simple math operations involving impulse and change in momentum. We're going to be doing it in the context of a table like you see here. And this table has some cells that are missing, and we have to figure out what is the missing answer. So to do this, we'll need to remember the momentum impulse theorem. I'm going to write that down here so that we all remember it. And that is force times time equals the change in momentum. There's a couple of other things we could write out to the side as well. We can remember that impulse is equal to the force times time, and that the change in momentum is the final momentum minus the initial momentum. So all four of these quantities are equal to each other. So using that information, we can do some quick math to figure out the missing information in this table. So the first thing we're missing is impulse. We have force and time. So if we multiply force times time, that'll give us the impulse. So 15 times 3, the impulse is 45.0 Newton seconds. If you remember, the impulse is equal to the change in momentum. And so these two are always going to be equal to each other. So that makes it pretty easy. We can just simply copy whatever's in one cell with the other. I can go ahead and do this for all the cells that have this already have one of these filled out, because these two cells are always equal to each other. The impulse is equal to the change in momentum. Now, it has here as this last column the final momentum. Usually we would need to know the initial momentum if we only know the change in momentum, but I skipped over the beginning, which is probably what a lot of you might do too when you're doing problems like this. I didn't read the actual information at the start here. It says an object is at rest, and then it experiences a force for a given duration of time, resulting in an impulse that causes a change in momentum. The final momentum is different than the initial momentum. In this case, it says the object starts out at rest, and so we can know that the initial momentum for all of these is 0. And so this, if we look down here at our initial momentum here, this is always just going to be 0 for these problems. And so what ends up happening is whatever the change in momentum is, well, that's going to be a change from 0. And so the change in momentum will just equal the final momentum in these examples. That won't always be the case because the initial momentum isn't always 0, but for these, it makes it pretty simple. These are all just the same as the previous column because the object started at rest. And that's true here too. So I can start filling in, doing a little puzzle work here. I kind of like this because it's like a little puzzle. You can, once you figure out the key, you can kind of work backwards and do a lot of these. So now I have more than half the table filled out. Now we got to do a little bit of, kind of the opposite working through. So before we can multiply force times time to get impulse, but now we're missing one of the force or the times. And so we're going to have to do some division. So to find the force, for example, if we want to find the force, it's going to be, if I look at this equation, I'm going to divide by time. So I take the impulse and divide by time. And likewise for the time is just going to be, let me scroll down a little bit here. The time is just the impulse divided by the force. So I'm going to need to pull out my calculator maybe to do part of this. Oh no, I'm in the way. So for the second row, my impulse is 20. I'm going to divide that by 0.0500. And so my force is 400. That needs to be 3 sig figs, so I'm going to do a little dot right there. I should write that in scientific notation, but I'll just keep it like that for now, and just to keep it simple. For the third row, we have 15 for our impulse, 15.0. Divide that by 60. and that gives us a time of 0.25. That's only 2 sig figs. I need one more, so I'll add a 0 at the end of that. All of these have 3 sig figs in here. And then for my last one, I have 16 divided by 0.8, and that gives me 20.0. And I can do a quick check of that and make sure if I multiply these two together, I should get the impulse in that second column there. So let's do one more table like this. So this one has a little bit more involved in it just because the initial momentum is not 0 anymore. But we're still dealing with the same setup, same problem here. Its impulse is equal to force times time, which is equal to the change in momentum, which is equal to the final momentum minus the initial momentum. Okay, so we can right away remember that these two, impulse and the change in momentum, are equal. So whatever one cell is, the other one will also be equal to it. Unfortunately, we only have one that we know of to go ahead and fill in, but we can quickly find some more here. For example, force times time is impulse. So we have a force of 10 newtons times 8 seconds. That's going to be an impulse of 80 newton seconds, 80.0 newton seconds. So we can write that over here as well, 80.0. Let's go ahead and find the final momentum for this first row. The initial momentum is 5, and we have a change in momentum of 80. So we started out with a momentum, initial momentum of 5, and the final momentum is our unknown. Our change in momentum is 80. And so to find the final momentum, we'll just add 5 to both sides here. So the final momentum is going to be 85.0. Now, I did all this algebraically, but you can also just think about it logically. If you start out at a certain momentum and then your momentum changes by this much, we're adding 80 to it, right? So we start at 5 and we add 80 as our change, and so our final momentum will be 85. Likewise, we can do the same thing here. If we start at an initial momentum of 6 and then we add 24 to that, 24 plus 6 is 30. Okay. You can do the inverse of that for these last two rows here. I'm just sticking with this final momentum for a little bit because if our initial momentum is 22 and our final momentum is 24, how much did our momentum change by? Well, the change is the final minus the initial, 24 minus 22. That means we have a change of momentum of 2 for this row, 2.0. And so that can also be written right here. Let's go backwards and do this second row. Let's find the missing time here. And so we have an impulse and we have a force. So we know force times something gives us the impulse. Force times the time gives us impulse. So 12 times something gives us 24. So we can do 24 divided by 12. That's going to be 2.00. Okay, we have another situation here where we have force times time is 2. Something times 0.500 gives us 2. We can just do this one in our calculator here, do it backwards. So 2 divided by 0.5, 0.5 is 4.0. So I've filled out the first 3 rows now. For this last one, we only have the force and the time, but we can multiply those together to give us the impulse. So 16 times 0.5 is 8.00. Same over here, 8.00. We have a change in momentum of 8. It also says our final momentum is 8. So we have a change in momentum of 8 and a final momentum of 8. That must mean that we started out at an initial momentum of 0 because we added 8 to it and our final momentum is now 8. You know, I can always check that by remembering the change in momentum is the final minus the initial, right? And so we knew that the change was 8. We knew the final was 8. So the initial is what we're solving for there. Excuse me. So kind of looks a little weird because we're just solving and we get 0 as our initial momentum. So that's it. That's all I've got for you in this video. So remember, a bad attitude is like a flat tire. Until you change it, you're not going to get anywhere.